Thank you, Mr. Chairman, and thank you, dear colleagues, for coming this morning after our great party. I will be very quickly, and after that we go to the breakfast. So, this is my talk, magnetic field influence on the penning discharge characteristic, penning discharge which used in ion source for miniature linear accelerator. And where is my presentation? Oh, thank you. So, the outline of my talk, first of all, I will tell several words about subject of our investigation and motivation of our research. Briefly, I will tell you about experiment setup, and more detail, I will tell you about configuration of various parameters of magnetic field configuration which we used. And the main part of my talk is experiment results and compare it with particle and cell simulation and conclusion. So, I work in Dukhov Research Institute of Automatic. Our institute produces neutron generation systems which can be used in many fields of technology or science, and one of them is pulse neutron logic method to find all gas in our Earth. So this is our neutron generation system, and the main part, the heart of this generation system is a gas-sealed neutron tube. What is it? It is a miniature linear accelerator with penning ion source, ion beam optical system, and neutron target. So here is our gas storage, which includes deuterium, tritium gases. When we heat it, they dissolved. After that, we have injection anode voltage pulse. Just a minute. Here our pulse, yes. Our device works in pulse periodic regime mode with big varies of time of pulse and frequency. And how you can understand, the neutron yield is proportional, in first estimation, is proportional to extraction current. Yes? So we have pulses and what we need. The global aim of our work is to increase the parameter of neutron, pulse neutron flux. So we need the more extraction current, we need to always increase amplitude of this current pulse. We need to less discharge current to increase the ion source efficiency. Also, for this neutron logic, it's very necessary to clear and identify the neutron pulse. So we need to sharp leading and trailing edges. So we need to delay time of front, and we need to decrease time delay. It's time between anode pulses and appearance of extraction current pulse. So, and what motivation of this part research? How we know is well known. It's well known for literature. Discharge current behavior depending magnetic field. You can see this graph. When we have anode voltage and pressure value as parameter, and it's a lot of investigation for vacuum gauges, for vacuum pumps, and there is a little bit information about extraction behavior in our device, is our small devices, I would say things like that. And also there is no information about pulse periodic regimes of discharge. So we didn't know what behavior of our time amplitude parameters. Also, what will it be if we choose non-uniform magnetic field? And also, I should mention to this fact that, our device couldn't change magnetic field during operation in the Earth. So we need to have dependencies of currents and and time on pressure, and the magnetic field with only like parameters. So with several our experimental setups, and we can see the links to reference. We can also compare it with particle sense simulation. And the main part of this work was done on this diagnostic complex, which can study the operation mode of Penning-kind source in a deuterium gas-sealed neutron tube with controlling pressure, controlling all current parameters. We could, if we need, we could control neutron flux and pressure. How do you say it? Okay. But it's a deuterium reaction only. So, what configuration magnetic field we used? How I say, we use solenoid to create magnetic field in our experiment. So we could change configuration and the value of magnetic field. And first of all, it's a uniform magnetic field with we have different value of magnetic field and non-uniform magnetic field, which we divided into parts. It's a slow decreasing non-uniform magnetic field, such kind of this, and rapidly decreasing uniform magnetic field, non-uniform magnetic field. So how can it see? This is cathode, it's anode. So the magnetic field decreases towards anticathode. In anticathode we have aperture to extract our ions. So experimental results. Please make attention in these slides. Here is discharge current and extraction current pulses obtained in different magnetic fields with constant pressure. So it's some kind of small, low magnetic fields, it's medium and it's high. So how can you see the shape of the discharge and extraction current? Discharge is black and extraction is red color, is significantly changed when we increase magnetic field. So the shape, in the first time we have some kind of triangle periodic spices. So in our application we couldn't use it. We need some kind of rectangular shape or quasi-trapezoidal shape of the pulse like this. But how can you see, with increasing magnetic field, the ion source efficiency of extraction is significantly decreased. So here we see extraction, discharge current, sorry, and here is only extraction. When we increase more times, we have significant increasing discharge current. And can you see here is about 1 or 2 milliamperes, and here we have 8 milliamperes of discharge current. And how can we see? We have two triangle periodic spice, and we have a little extraction coefficient, and one more. In this case, we have additional delay time between discharge current and extraction current. Here, how can you see when discharge appears? We have already see extraction current, and here some additional delay. So it's almost the bad operation mode for our application. I'm sorry. We look for average currents, yes, which can is some average current of our pulses, yes. And the independence of discharge average current, how can you see in this left picture, is the same how I already show you. It's sharp growth, and when it decreases during increasing magnetic field. But how can we see the extraction current in all pressure mode have two special maximums and one gap. So it means that in this part of, please see the red line. In this part we have triangle shape of the pulses, where we go to the rectangular shape of the pulses, the average current is decreased. After that, it's increasing with increased magnetic field, and then we have once more triangle pulses, the average current goes down. Here, how can you see, we have dependence, what we want, dependence of average currents depending on pressure in with magnetic field like parameters. Here you can see it. What can you say? And what we can receive, the magnetic field intensity increase, significant increase with increasing magnetic field. How can you see? Is the more when one order. How can you see? Look, please. For example, in the blue line is for 90 millitesla. When discharge is burned, we have rectangular shape and here region. Then after that we have some transition mode, and after that we have linearly increasing discharge current with increasing pressure with rectangular form of the current pulse. But if we see the extraction current behavior, there is no significant increasing in extraction current. How can you see it? And it's increasing only 2, maybe 3 times. What about time? Time delay, how can you see? With increasing magnetic field in first time, it's go to degrees. It's very good for us. But after it's about 100 millitesla, it stops, and we have, how can I say, a problem with with ignition. So it's unstable discharge mode regime. There we have our triangle periodic spikes. Okay. And time delay. I briefly show you particle and simulation results. How we can see this graphs obtained by particle and cell? It's a good general view of this. Is very similar to our experimental source, but we have some differences. First of all, it's too high amplitude and without time delay. We confronted with our computation mesh, a small total number of particles and big initial particles. I can show you the electron and ion distribution on a transverse plane which crossed the center of the anode. So it's electrons, ions in this period of time. So if you have unstable form, concentration of electrons goes sharp, and we have a big accumulation of volume charge. So they want to move around this spot, want to move around the axis, but it shouldn't happen. The electric field push the electrons to anode and destroyed this plasma formation, and it only starts. Some of electrons are left, and this behavior starts again. In stable mode, how can you see the electron in much more magnetic field level? The electrons are not evenly distributed and occur only one part of anode, and in first moment of time they started around the axis with big speed. So the concentration of electrons stop growth and have a stable form which always moved. And the ions, how can you see, it's have good distribution, and it didn't change anymore. Very quickly about a non-uniform magnetic field. So it's, how can I say, slow decreasing and rapidly decreasing magnetic field. Very quickly. How can you see the discharge current There is no significant increased discharge current in this case of this. We have a good linear dependence of extraction current depending on pressure. We have good extraction coefficient. How can you see? It's about 40 or 50%. We have more better time, amplitude time characteristics, so we can decreasing delay time to 10, up from 10 to 5 microseconds, and time front is more than 1 microsecond. So for our applied application, for our ion sources which were used in neutron tube, we have some recommended boundary of magnetic field configuration. So if it's higher, we have the bad extraction current shape, and we have small efficiency. So if we below this boundary, how can you see, it's time delay which very big, and shape also awful. And if we have here, we have a good shape of the pulses. Oh, parameters is good. Okay, we win it. So, in summary of my talk, we have experience with different magnetic field configuration. We could see the stable and unstable discharge more depending on magnetic field and pressure. So if we use non-linear magnetic field in ion sources, it will be better for extraction current and amplitude time parameters. Thank you for your attention.